Welcome to Math 2320, Section 2.6. In this particular section, we're looking at a numerical technique called Euler's method. The idea is the following. We're given some initial condition. Based on that initial condition and the flow field, our function which has the arrows that we saw in previous sections around the plane here. Euler's method will allow us to step based on a step size starting at our initial condition to another point, and then we'll step to another point and then step again depending upon the step size. So it's based on the initial condition where we start and the flow field, because the flow field, as we saw in previous problems, is very different in different places. So the basic iterative method is yn plus 1 is yn plus h is my step size, and f of xn, yn, that's our flow field. So we're going to have a starting position, a step size, and in this problem we have two different step sizes. Our differential equation is here. Y prime is 2x minus 3y plus 1. So there's my flow field. And my initial condition is y at 1 is 9. And we're wanting to get to y of 1.2. Alright, so let's see how this works. Alright, so I've done it two ways. One way is by using Wolfram Alpha. You can type in use Euler method, put in your differential equation, initial condition from where we're starting to where we'd like to end up, and you tell it the step size. And when you do that, it's going to produce a table like the following. So here we are at step 0. We're at 1, 9. We take one step forward, which is 0.1 forward, and we get 1.1. Another step forward, and we are at 1.2. And the value of y at each of those points is given there. Alright, so let's see this by hand. So y1, my very first one is y at 1.1. That's my new x1. And it's based on y0 plus my step size and then f of the initial conditions. Alright, so y0 was 9. Step size is 0.11, and I'm putting 1, 9 into my vector field, my flow function. When I do that, I get a minus 24, and so I get 9 minus 2.4 or 6.6, and that's exactly what we have in the table there on the left. So now we take one more step forward. Alright, so that's x equals 1.1 where we left off, plus our step size, which will take me to 1, 2. So y at 1, 2 is y2, which is y1 plus my step size 0.1 times f at my new position. So that's at 1, 1, 1.1, and 6.6. So again, we're stepping through the flow field. Alright, so y1 is where we left off, which was 6.6. Again, I plug in these two numbers into my flow field, And when you grind through all that, you get minus 16.6. Multiply that by zero point 0.1, and so I get 6.6 minus 1.66, and I get 4.94. So we essentially made two steps in this process. Now, if you're looking to program this, which many of you will, those of you who are engineering majors, one of your first courses in engineering is typically a programming course. That could be in MATLAB, it could be in Mathematica, it could be in a program language like Java or C. So let's see here. Yn plus 1 is Yn plus hk1. Well, what is this k1? Well, k1 is our particular vector field. And so that's where they're showing us that. All right, and so we can step through and you iterate the process using a computer where you would make the step size smaller and you can make a lot of steps. In the second half of the problem, the step size is halved and now it's 0.05. And so again, I did this in Wolfram Alpha to show the steps and the various outputs. My function's still the same. The process is still the same, just longer and more tedious. So x1 is 1.05. My initial position was 9. Step size is now 0.05. I still plug in 19 to start. We're just stepping smaller. So by doing that, I get y at the new position is 7.8. So now to get your next x, you again add a step. All right, so that puts it at 1.1. And so now y at 1.1 is y2, and so that's y1 plus h, and now f at x1, y1. Where we left off was 7.8, and now I need my flow field there at 1.05, my x1 and y1. And when you grind through that, you get your new y2, which is 6.785. I step another h, and so that's 1.1 plus 0.05 or 1.15. So the process is the same, it's just longer and much more tedious. That's why it's good to do a few of these by hand, but if I wanted to do 1,000 or 10,000 steps, I certainly would want to use the computer. But doing it by hand, if you check the numbers that I finally ended up with, these are the same numbers that you see in the table up here that we created using Wolfram Alpha. So it's good to do some of this by hand so you get a feel for what's going on. It's also good to see how to do it in a particular software package. In this case, this was with Wolfram Alpha, but you could certainly do it in Mathematica or MATLAB or even program it in a programming language.